Hi, I'm Emma. I'm from Louisiana State University. So the talk I'm going to be giving today is higher reciprocity laws, modular forms of weight one, and their Galois representations. I'm glad to be here. Thank you for having me. Uh, but yeah, so I'll just start. But So to start with some preliminaries, given a finite index subgroup gamma of SL2 of Z and a non-negative integer k, we define a weight k modular form as a function from the upper half plane to C, such that it satisfies the following properties. So the function f is holomorphic. For any matrix in gamma, we have this matrix action on the upper half plane, and it satisfies this relationship here. And the third condition is that the function is still holomorphic as tau approaches imaginary infinity. So with odd weights, a complication arises in that all odd weight modular forms vanish for a certain gamma. So we have to modify this by introducing a Dirichlet character. So for the rest of the talk, you can just assume chi to be the Lejeune character, as that's the only character we'll be dealing with. And the second property transforms into basically the same thing, but now we have this chi of D in front of the relation. So this will allow us to look at non-zero weight one modular forms. So a large problem in number theory is that of reciprocity. So quadratic reciprocity essentially says that if you have a quadratic polynomial, it tells you when it's irreducible mod p for any given prime and when it splits into linear factors. So you might have seen this example before, that x squared plus 1 splits mod p if and only if either p is equal to 2 or p is 1 mod 4. And sort of ignoring this case, which is the case for ramified primes, all other primes can be fit into this, all other primes for which x squared plus 1 splits can be characterized by this modular congruence. So we would hope that this can be generalized to higher degree polynomials. So for any polynomial, we could describe some set of modular congruences such that the polynomial splits if and only if the prime satisfies these congruences or it's ramified. But that's not the case. As class field theory in part says that the splitting behavior of a polynomial can be described with modular congruences if and only if the splitting field of the polynomial is an abelian extension. So for quadratic polynomials, every quadratic polynomial, the splitting field is just a quadratic extension, and the Galois group is always Z mod 2, which is always abelian. So it always works out in that case. But if you go even to cubic polynomials, you can have cubic polynomials whose splitting field is S3, which is non-abelian, and you run into some issues there. So this project follows the work of Toyokazu Hiramatsu in his paper, Higher Reciprocity Laws and Modular Forms of Weight 1. So in this paper, he works with a specific kind of product of Dedekind eta functions, of the Dedekind eta function. And he shows that this particular class of eta products is actually all, actually form weight one modular forms. And he proves the following theorem. So the polynomial x cubed minus x squared minus x minus 1 splits mod p if and only if the Lejeune character of p over 11 is 1 and c of p is 2. So c of n is defined as the nth coefficient of the Fourier expansion of this eta product, which is a modular form. So if we want to determine whether this splits mod p, all we have to do is look at the coefficients and look at whether it's a square mod 11. So if we look at the first few terms of the Fourier expansion, the first time that we have a coefficient equal to 2 is for p equals 47. And luckily enough, 47 is a square mod 1. So if we look at the factorization of this polynomial, mod 47, we see that it actually splits into linear factors. So when the coefficient is 2, that should correspond to the polynomial splitting into linear factors, mod that prime number. And different coefficients sort of correspond to different behaviors. If the coefficient is 0, I think it should correspond to being irreducible, I think. And then if it's -1, it should correspond to factoring as a quadratic times a linear factor. So the significance being here to what I was saying before is that the splitting field of this polynomial is S3. So we can't really describe it using modular congruences, but we can describe the splitting behavior using the coefficients of this modular form. So the question I had in mind is, given a modular form of weight 1, how do we find the polynomial that it corresponds to? So he gave a couple examples in his paper, and so I want to look at the other examples that he did not actually prove. So there are a few important aspects with working with weight 1 modular forms that makes it work out well. The most important being this theorem by Serre and Lien, which says that given a normalized weight 1 Hecke eigenform of level NF, there exists a finite Galois extension and a two-dimensional complex Galois representation, rho F, such that for any prime not dividing the level, we have that the pth coefficient in the Fourier expansion of the modular form is the trace of rho F of the pth Frobenius. So a subtle but important point is that given a weight 1 modular form, we first have to check if it's a Hecke eigenform. And there's a somewhat amusing anecdote of when I was working all of this out, I spent about 2 weeks trying to prove that this, trying to find the polynomial that corresponded to the certain modular form. But it turns out it wasn't even a Hecke eigenform to begin with. So I wasted 2 weeks because I forgot to check one of the most basic things in order to apply the theorem to begin with. So in his paper, there are 7 Hecke eigenforms. So of the ones he proved, there are 4 of them that he proved in his paper, and the remaining 3 are eta of 3 tau times eta of 21 tau, eta of 4 tau times eta of 20 tau, and eta of 6 tau times eta 18 tau. So we want to find polynomials that sort of correspond to each of these so that we get a sort of analogous theorem to the one that he proved in his paper. So for each of the modular forms, there's a corresponding imaginary quadratic extension, which is a subfield of K, which is the Galois extension that we want to find. So by the theorem of Serre and Lien, properties of GL2 of C, and the fact that the modular forms have integer coefficients, we can actually deduce that the orders of Frobenius elements are 2, 3, 4, and 6. So the Galois group only has elements of order 2, 3, 4, or 6, and that restricts the degree of the overall Galois extension. And since it's a finite extension, the representation is completely determined by the traces. So for the case of eta of 4 tau times eta of 20 tau, we can show that the coefficients are even. So all the elements of the Galois group have even order. So this should correspond to an even degree Galois extension. And in this case, I believe it's a quartic polynomial that corresponds to this modular form. So knowing that the ramified primes divide the level and that the Galois groups in these examples are dihedral, we can use a database and just sort of take all of the information we know about it and just start testing from a relatively small number of Galois extensions and see which ones actually match with the coefficients of this modular form, since we know that the coefficients of this Fourier expansion should correspond to the traces of some Galois extension, Galois representation. So in a similar manner, examining the coefficients and narrowing down polynomials in a database, we have the following candidates for polynomials that correspond to the modular forms, which we can then prove. So for 3 and 21, we have x to the fourth minus x cubed plus 2x plus 1. For 4 and 20, we have x to the fourth plus x squared minus 1. And for 6 and 18, we have x cubed minus 2. So the proofs actually follow similarly to how he proved it in his paper. So on the side of the modular forms, we can use basic modular arithmetic to relate the coefficients to some quadratic form related to the imaginary quadratic subextension. So if we looked at the Fourier expansion of the 2 and 22 case, we see that in this exponent here, we have sort of a quadratic form here. And this is the quadratic form that I'm referring to when I say that we're going to link, we're going to determine the coefficients by looking at this quadratic form. And then we're going to take the polynomial and the Galois, the splitting field that we sort of guessed was our match. And we're going to use class field theory to actually prove that the primes that split in that splitting field actually correspond to the this quadratic form. So the case of eta of 6 tau times eta of 18 tau is particularly nice, as the Galois extension side just sort of follows from cubic reciprocity. So to run through this eta 6 tau times eta of 18 tau case, we can take the Fourier expansion of this, and as I mentioned before, we have this quadratic form in the exponent. So the pth coefficient relies heavily on the number of solutions to 4p equals this something squared, something that's 1 mod 6 squared plus 3 times something that's 1 mod 6 squared. So if p is equal to a squared plus 3b squared for some integers a and b, we have these two solutions to the equation. And up to a sign, these are the only solutions to the equations. So there's 8 solutions, but we need to specifically pick solutions that are 1 mod 6. So if we have that each of these is 1 or 5 mod 6, then we can just change the sign to specify that it's 1 mod 6. So first we need to determine if these are 1 or 5 mod 6. This a minus 3b, a plus b, and so on. So since p is 1 or 5 mod 6, we're assuming p is not 2 or 3. A squared plus 3b squared, which we can factor mod 6 as this. And that has to be equivalent to 1 or 5 mod 6. But these are units, so that means these have to be units as well. So if 3 divides b, we can actually take appropriate signs so that all of the solutions are 1 mod 6, and we end up with 2 solutions. But if 3 does not divide b, exactly one of either a plus b or a minus b is going to end up being 3 mod 6. So we have to throw out one of the solutions, and we end up with only one appropriate solution. One appropriate solution. So the sign of the coefficient is then determined by noticing that u plus v is even if and only if 6u plus 1 is equivalent to 6v plus 1 mod 4. So to determine the sign, we look at what these are, mod 4, and if they're equivalent mod 4, then the sign is positive, and if they're not equivalent mod 4, then the sign is negative. And it actually works out pretty nicely, so that if both solutions work and we have 2 solutions, then we have that the sign of the coefficient is positive. And if it's only one solution, then the sign is negative. So it's C of p, the pth coefficient, is 2 if and only if p is equal to a squared plus 3b squared, with b a multiple of 3. which you can also represent as P being equal to A squared plus 27B squared. But if you know a little cubic reciprocity, this is precisely the primes in which x cubed minus 2 splits mod P. So this has to be the desired polynomial. Thank you.